Let's continue our discussion of atomic theory and the quantum model of the atom by reviewing the concepts of isotopes and the atomic mass number that can be found on the periodic table. This notation should be familiar. The Mg is simply the symbol of the element, in this case magnesium. The number in the upper right-hand corner represents the mass number. The mass number is the number of protons plus neutrons in the nucleus of this atom. The number in the lower left corner of this notation is the atomic number. Remember that the atomic number is the number of protons by definition. However, in a neutral atom, the atomic number also represents the number of electrons in that atom. So how many protons does this atom of magnesium have? Well, it has 12 protons. How many neutrons does it have then? Well, here we got to do a little math. We know it has 12 protons, and we also know that it has 25 protons and neutrons. So if we take the mass number and subtract the atomic number, we will get the number of neutrons in the nucleus. 25 minus 12 is 13 neutrons. As we know, if an atom is neutral, the number of protons and electrons have to be equal. So if there's 12 protons in this magnesium atom, then there must be 12 electrons in this magnesium atom. Now this magnesium atom is just one of many isotopes of magnesium. Remember, isotopes are elements that have the same atomic number but different mass number. Any atom that has 12 protons is an atom of magnesium, but those atoms of magnesium could have different numbers of neutrons. That would give them a different mass number. So atoms with the same number of protons but different numbers of neutrons are isotopes of each other. I've listed a few of the isotopes of magnesium here in this table. There are actually 22 different isotopes of magnesium, and you can see that by referring to a very useful website known as ptable.com. Let's take a quick look at this website, ptable.com. You can see at the top there are different menus you can select to analyze a periodic table. I have the isotope menu selected here. So if I go to an element and click on it, like magnesium, it'll pop up and show me all the different isotopes of that atom. So there are 22 different isotopes of magnesium. However, only 3 are stable. They're the only ones that are found in any type of abundance on Earth. The other isotopes are very short-lived. So here are the 3 isotopes of magnesium that are the most abundant. We've also listed their actual atomic masses for those isotopes. We're going to use relative abundance and the atomic mass of each of these isotopes to determine the actual atomic mass that you see on the periodic table. So the atomic mass is an average of all the masses of the naturally occurring isotopes of an element. So if we were going to determine the atomic mass as it appears on the periodic table, we need to take the natural abundances and multiply by the actual mass of those isotopes, and then we just add them together. So we know that magnesium 24 has about a 79% abundance, magnesium 25 a 10% abundance, magnesium 26 an 11% abundance. I'm going to change those to a decimal by dividing by 100. So those become 0.789, 0.1, 0.1101. I'm going to take those decimal forms and multiply now by the mass of each of those isotopes. So the first one gets me a mass of about 18.9. When I do the second multiplication, I just have to move my decimal point over one spot to the left if I multiply by 0.1, so I get about 0.25. For the last one, I'll take 0.11 times 25.98, blah, 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 and I get 2.860, blah, blah, blah. So what I have to do now is add those numbers together. I'm not rounding until I get all the way done. So when I add those numbers together, I get 24.3050503. Now, finally, I'm going to round this to the tenths place. That gives me 24.3. If I look at my periodic table, I can see that the atomic weight is the lower number in the periodic table, the one that has the decimals. So if I look up magnesium on my periodic table, I would see it has a mass of 24.305. If I round that to the tens place, I get 24.3. So the value I calculated by using my abundances and the actual masses of the isotopes is equal to the mass that I got on the periodic table. That's pretty dang good. But the masses on the periodic table come from an average of all the different isotopes of that possible element. So we know where the atomic number is in a box on the periodic table. We now have a little bit better understanding of where the atomic mass comes from in every box on the periodic table. Let's talk more about the periodic table in general. First of all, it should look something like this. The two rows that are often placed underneath the periodic table should be inserted in here between the transition metals. These are the lanthanides and the actinides. However, this makes the table really large and hard to print on a 8.5 by 11 sheet of paper. So oftentimes those two rows are taken out of the table and placed underneath. There are 118 boxes on this periodic table if you were to count. We've come a long way since 100 AD when there was only 9 known elements, including copper, silver, and gold. But even then, 1900 years later, scientists only knew of 26 elements. As technology improved, over the next 100 years, they were up to 81 elements. Over the next 100 years, up to 115. And now, like I said, in the present day, we have the whole table filled out. We know of the 118 elements that would fit on this periodic table. If you know me, you know I'm a pretty big nerd as far as the periodic table goes. It's an amazing accomplishment, and it gets so much information from it. The first person that gets credited for developing a periodic table is Dmitri Mendeleev. Okay, he arranged his periodic table by increasing atomic mass and used similar properties to place those elements in regular intervals. We now know that the periodic table is arranged by increasing atomic number. Okay, the periodic table is simply an arrangement of the elements that places them in a repeating pattern based on their physical and chemical properties. The properties of elements and their compounds are periodic functions of their atomic number. That simply means there's a repeating pattern to the properties of elements and their compounds. On the periodic table, there are 3 different classes of elements: metals, nonmetals, and metalloids. There are way more metals than nonmetals, or 89 metals. If you go across a period on a periodic table, the metals decrease in activity. They are not as reactive as you go left to right across a period. As you go down a group or a family, though, the metals become more reactive. There are 19 nonmetals. Their activity is actually the reverse of metals. Their activity increases as you go from left to right across the period, but it decreases as you go down a column or a family. The metalloids are the elements that separate the metals from the nonmetals on the periodic table. There are 7 of them. They include boron, silicon, germanium, antimony, tellurium, astatine, and arsenic. On your periodic table, you may have drawn in the staircase. The staircase separates the metals from the nonmetals, and the metalloids are located on that staircase, as you can see here. The metals are on the left side of the periodic table, and the nonmetals are on the right side of the periodic table. Hopefully you remember that periods are the rows of the periodic table. Hydrogen and helium make up period 1. Lithium starts period 2. Period 2 ends with neon. Sodium to argon is period 3. Potassium all the way to krypton is period 4. Rubidium to xenon is period 5. Cesium all the way through radon is period 6. And francium all the way through oganesson is period 7. Families or groups are in the columns of the periodic table. You can see the different families labeled at the top of your periodic table. The most reactive metals are alkali metals found in group 1. The next most reactive metals are in group 2, and they're known as the alkaline earth metals. The most reactive nonmetals are found in group 7. They're known as the halogens. And remember, the noble gases are in group 8, and they are unreactive for reasons we will explain here shortly. Transition metals can be found in this block in the middle of the periodic table. So let's talk about those noble gases for a second. Noble gases are not reactive under normal conditions. There's a reason why they're not reactive, and that is because they have a filled valence shell. There's no need for them to gain or share or lose electrons in order to get a full valence shell because they already have a filled outer shell of electrons. Let's take a look. If we look at this isotope of helium here, we know that isotope has 2 protons. We also know it would have 2 neutrons because the mass number is 4. So 4 minus 2 would be 2 neutrons. Since helium has 2 protons, we know helium has 2 electrons. Its electron configuration would be 1s2. And that just so happens to fill up the first energy level. So helium has a full first energy level, a full valence shell. Neon has 10 protons, and this isotope of neon happens to have a mass number of 20, so 20 minus 10 means this isotope would have 10 neutrons as well. If you do the electron configuration of neon, you get 1s2, 2s2, 2p6. Well, the second energy level is its valence shell, and you can see it's full of 8 electrons. The electrons in the first energy of neon would be known as the core electrons. But neon has a full outer energy level, just like helium does. Therefore, it's not reactive. Let's do one more. Argon has 18 protons, and this isotope of argon would happen to have 22 neutrons because 40 minus 18 is 22. The valence shell for argon would be 3. It's the outermost energy level. And you can see it has 2 electrons in the s orbital, 6 in the p orbital. It has a full valence shell. Full valence shell means it will not be reactive. There's no need for it to react. The core electrons for argon would be in the first and second energy levels. But every single energy level is filled up. There's no reason for these noble gases to react with other elements in order to achieve a full valence shell, so they are unreactive. Let's look at some of the repeating properties that can be seen on the periodic table. Let's start with atomic radius. Atomic radius is basically how big the atom is. We're going to measure it in picometers. If you use ptable.com, you can select the Properties tab at the top, and you can explore all the different periodic trends that can be observed using the periodic table, including the atomic radius. So if I'm looking up these values on ptable.com, I would be looking at the calculated radius, and you can see it's measured in picometers. For a family or a column on the periodic table, the size of an atom increases because you are adding on another energy level for electrons to occupy. The core electrons shield the valence electrons from the positively charged nucleus, making the atom get bigger. The nucleus can't hold on to those electrons as tight. So if you look at the trend for the alkaline earth metals, you can see that the atomic radius increases as you go down the family. Across a period, you're adding electrons to the same energy level. So as you add an electron, the nucleus also has another proton. So you're getting one more proton and one more electron. So the attraction between the nucleus and the electrons becomes greater. And the size of the atom, therefore, becomes smaller. So as you go across a period, atoms actually get smaller in size. If you look at period 3 across the periodic table, the atomic size decreases from sodium to argon. Now, since atomic radius is a periodic trend, we should be able to make a reasonable prediction as to what the atomic radius of radon would be, the one I did not list. So if you compare calcium and strontium, you can see there's a change of about 25 picometers. And then if you go from strontium to barium, there's a change of about 34 picometers. So it's reasonable to say that you might get a change in atomic radius of about 8 or 9 additional picometers when you look at radon. So a good prediction for the atomic radius of radon might be about 295. Just add 253 plus 42. Ionization energy is also a periodic trend that can be found using ptable.com. All you would have to do is look up the property of first ionization energy, measured in electron volts. Ionization energy is exactly what it sounds like. It's the energy needed to create an ion, to remove an electron from an atom. The types of elements that would have low ionization energies would be metals, especially family 1. That's because they only have one valence electron, which means those electrons are furthest away from the nucleus, therefore easier to remove. You can examine this for yourself by looking at the ionization energies down family number 1, the alkali metals, on the periodic table. You can see that the ionization energies are pretty small, and they also decrease as you go down the table. Nonmetals are going to have high ionization energies, especially noble gases. Why is that? They have a full valence shell. Removing an electron from that type of an atom is going to be very difficult because there's such a large attraction between the positively charged nucleus and the electrons in the electron cloud. If you take a look at the ionization energies for the noble gases, you can see they're much larger than the ionization energies for the alkali metals. But you can still see the trend that the ionization energy decreases down the family. Okay, let's predict what the ionization energy would be for oganesson, since this is a periodic trend. We can do a similar thing to what we did with the atomic radius. We can see that there's a change of about 1.9 in ionization energy from krypton to xenon. We can see from xenon to radon there's a change of about 1.3. So it'd be reasonable to predict that there's going to be a change of about 1 electron volt as you go from radon to oganesson. So a reasonable prediction for the ionization energy of oganesson would be 9.7. So let's consider the ionization energy across a period. In this case, we'll look at period 3, comparing sodium, magnesium, and aluminum. Here are the electron configurations for those elements. We also have the ionization energies for removing the first electron from these elements, the second electron from these elements, the third electron from these elements, and then the fourth electron from these elements. Okay, you'll notice that there's a large increases in ionization potential as electrons are removed. For example, if I take away the first electron from sodium, it's relatively easy. But trying to remove the second electron, all of a sudden there's a large jump from 5.1 electron volts to 47.1 electron volts. That's a ridiculous jump in energy. Why is it so much harder to remove that second electron? You'll notice a similar trend for magnesium, but this time the big jump occurs after you remove the second electron. It goes from 15 electron volts all the way up to almost 80 electron volts. Why is that happening? You'll notice another similar trend for aluminum. Doesn't require a lot of energy to remove the first electron. Second electron's not that bad. Third electron's not that bad. But then all of a sudden it jumps up from 28 to 119. Why are we getting these large jumps in ionization energy? Why is it harder to remove those electrons? So what's going on? Why are these big jumps happening? Well, at this point, you are trying to remove a core electron from the atom. Core electrons are closer to the nucleus, therefore they are much harder to remove because there's a larger attraction between the electrons and the nucleus. Okay, sodium has 1 valence electron. Magnesium has 2 valence electrons. Aluminum has 3 valence electrons. After you remove those valence electrons, you're down to core electrons. Core electrons are much harder to remove from the atom than valence electrons are. So that's why you get these big jumps in ionization energy as you go from a valence electron to a core electron. Okay, that's a lot of information about the periodic table. Take some time, wrap your head around it, and we'll see you again.